Now, with the fundamentals of TCP packet format, TCP being bidirectional, and we're actually counting bytes instead of packets. So with these out of the way, we can now come back to talk about the reliable data transfer mechanism implemented in TCP. Before Polly shows you the finite state machine of TCP's RDT, let's define this thing first. It's called the timeout interval or timeout value. Now, TCP being implementing a reliable data transfer protocol, it needs to also define this thing clearly. What is that? If you recall back and go back in, we said that after packet gets transmitted, we start a timer. That timer is going to tick, tick, tick. If an ACK does not come back before that timer expires or that timer times out, then what? We retransmit packet. So this timer there is to allow us to decide whether a packet is lost inside the network. So it's part of the RDT mechanism that is very critical. And that interval determines how long the retransmission is going to go. And that influences the performance of the reliable data transfer. We know already in some earlier example, if that timer is set too short, yeah, so packet can sometimes travel the internet a bit longer than usual. If that timer is too short and expires, then retransmission right before ACK arrives back, then this retransmission there is unnecessary and premature. Okay? That is not a good thing in terms of bandwidth consumption. So, not good. If that timer is too long, yeah, the intuition also says it's going to take a long time for the sender to discover there's a packet loss and try to recover from it. So you see that the user experience with sending data over this connection is not going to be good. Okay, so slow reaction to packet losses. Either case, not good. So how do we find a balance? How do we set or how do we estimate the timeout interval? You see, it's not that far-fetched. You heard Polly saying this already. The interval should at least cover what? The time data travel to the receiver and the ACK coming back from the receiver. And we know this is called what? The round trip time. But you also heard Polly saying that sometimes it takes longer for the data or ACK packet to travel the internet. Therefore, the timeout interval there should be set to cover longer than most of the round-trip time that the pair of sender-receiver might experience. And that is the idea behind how TCP estimates the timeout interval. And you see also, in TCP, it needs to observe the round-trip time repeatedly in between the pair of sender and receiver. Right? And this is exactly how it's done. For a pair of data goes out and the ACK come back, it calculates the time differences between receiving of ACK to the sending of data, and we get a simple RTT. Now, there will be a lot of these simple RTT for each data and ACK pair, but we will ignore the data ACK pairs due to retransmission. So some of these data might get lost and therefore they get retransmitted. When we receive an ACK for such a data, it could be a bit confusing, right? What is the right data sending time to subtract in order to be sure that this is really estimating just the round trip time and not covering a premature timeout, things like that. And we get lots of these simple RTTs, and they could vary quite a bit. So you see that it's actually not good to use the sample RTT as the timeout interval for the next packet. Not good. So what TCP does next is this, to get a smoother estimation of the round trip time. Okay? And that is done by taking the average of multiple recent sample RTTs. So what Polly brings up here is essentially the line of code in TCP's implementation, estimating the smoothed RTT. So the estimated RTT, this variable is to refer to the smoothed RTT. Now the smoothed RTT next is going to be the smooth RTT now, and take a weighted sum of that to the current sample of RTT. Okay, so current smooth RTT, and take the weighted sum of that to the current sample RTT. Okay, so we're taking the history into consideration, that's why it's called the moving average, and we're using a special factor alpha here, so it's a weighted moving average as well. Now the reason that it's called exponential is because of this, right? So the whole thing is the current, okay, smooth RTT. Now this whole thing is going to be used as what? The first term of the next estimation. So you see, okay, the current smooth RTT is going to be weighted what? 1 minus alpha, actually, 2 times. So the current estimated RTT 2 rounds later will weight exponentially less. Okay, 3 times 3 exponents less, 4, and so on and so forth. So the past sample, the influence of it will decrease exponentially fast. Okay. Oh, and by the way, alpha is only 0.125. That is because, yeah, we don't want to weight too much on the instantaneous RTT, because otherwise it will be what? Also fluctuating, okay, not exactly smooth. And here shows, yeah, the instantaneous RTT and the estimated RTT, the smooth estimation, how they look like relatively. And this is actually actual measurement between UMass and Eulercom again. Okay. So the blue one that fluctuates more, yeah, like these. Yeah, these are the instantaneous RTT, the sample RTT. The pink one then is the estimated RTT, the smooth, the average RTT over time. So you see that although the blue one fluctuates a lot, but the pink one, yeah, relatively smooth. And you see also, yeah, generally as time goes along, the round trip time tends to be longer. And so you see the pink here, yeah, the smooth average RTT is tracking the increase of the RTT relatively well. But be careful here. The estimated RTT is definitely not quite yet the timeout interval used by the TCP. Because if you do, you see these guys here, yeah, the round trip time is actually way longer than the timeout interval. So for all these guys, you will get premature timeouts. So the estimated RTT there is certainly not covering most of the round-trip time observations. So there's more. Therefore, in TCP, the exact timeout interval, okay, is in fact the estimated RTT, the smooth average, plus a safety margin. Okay. The safety margin there should cover the variation of these RTTs, and hopefully a good portion of the variations. So if we have a large variation in the estimated RTT, we should use a large safety margin. Okay. So this safety margin is captured by another variable called the deviation of RTT, DEV RTT there. And we are again, okay, borrowing this technique called the what? Exponential weighted smooth or moving average. Okay, so EWMA again, okay, to estimate the deviation of round trip time. What is the instantaneous deviation? Well, it will be what? The current instantaneous RTT subtracting the current smooth RTT. So this is the deviation of the RTT to the average. Okay. And so current sample weighted sum by the history of the deviation will be the next deviation of RTT. Okay. Now in this part, the alpha is set typically to 0.25. Okay. This is again, we don't want to weight too much on the instantaneous RTT, but the variation is relatively less fluctuating than the instantaneous RTT. So, yeah, so this is actually higher than 0.125. And most of the exact values we're setting for TCP are actually the result of estimation, measurement, and then deriving the best alpha and best beta. So people just borrow from other people's study and using these parameters accordingly. So finally, the timeout interval there is the estimated RTT plus 4 times the deviation of RTT. Okay, so safety margin covers the deviation, okay, the variations of RTTs. But the timeout interval is actually what? The average plus 4 times the deviation. Oh, what does that mean? So 4 here, seemingly randomly chosen, but if you recall statistics, okay, your first lesson of statistics, there's this thing called the what? Normal distribution. Yeah. In order to cover 99% of the samples, you have to add, okay, average to 3 times the standard deviation. So adding 4 times standard deviation is to cover way more than 99%. Okay, so this is also saying what? TCP is setting the timeout interval such that it covers 99.9 something percent of the RTTs. So we are very safe. Using this timeout interval, only a very small portion of the packets, the timers, will time out prematurely. That will save us a lot of what? Bandwidth for unnecessary retransmission. Therefore, in TCP, the timeout interval is the estimated RTT plus a safety margin. So estimated RTT is the what? The average. And the timeout interval should be the average plus a safety margin there, such that all these simple RTT fluctuates in the middle will be covered. Or, yeah, the more simple RTT being covered by the safety margin, the better. Challenge next is to set the safety margin. And the thinking behind setting the safety margin is this. If the sample RTT fluctuates a lot, yeah, we use a larger safety margin, right? Small fluctuation, smaller margin. Therefore, the key is to estimate the variation of the sample RTT. So the challenge boils down to estimate the variation of sample RTT. And that can be done this way. So sample RTT is the instantaneous RTT. And estimated RTT there is the variable storing the average RTT. So the deviation is essentially what? Yeah, the sample RTT subtracting the average RTT. All right? Now, of course, we will not be using this by itself to set the safety margin, because this is also what? The instantaneous deviation, right? So let's estimate the smooth deviation of round-trip time, okay, by the EV-RTT, and borrowing again the technique, the exponential weighted moving average, to get the smooth depth RTT. So the next depth RTT will be the current depth RTT and the weighted sum of that to the instantaneous deviation of RTT. Alright, so the only thing left is just the beta factor, and it's also set to a small value so that we weigh less on the instantaneous deviation. As to why it's 0.25, not 0.2, not 0.125, yeah, these alpha beta values are usually given because people have been using these values and they seem to work out fine, and engineers later on will just borrow using the same setting. And now finally, the timeout interval. It is the estimated on-trip time plus the safety margin, which is determined by the deviation of round-trip time. Now, as to why 4 times the deviation of round-trip time, the original designers of TCP, they don't usually talk about this. I mean, the 4 could be a result of repeated experiments. But Polly guessed also it could be because of this. They've assumed the simple RTT distribution being normal. If you recall back in Statistics 101, right? Normal distribution is for a sample such that if you plot the histogram of that sample, you see a bell shape. The average is usually in the middle where there are lots of samples. And the two ends, few samples. In normal distribution, starting from the average, if you add 2 standard deviation, subtract 2 standard deviation, it should cover what? 95% of the value range of all these samples. So by adding 4 standard deviation here, timeout interval here is covering more than 99.99 something percent of these sample RTTs. That is also saying, setting the timeout interval this way, there's going to be very few premature timeout in TCP.